Okay, we're going to keep looking at applications of derivative today. So we're going to be looking at what rates of change are. This problem wants us to find the average rate of change. Okay, we've talked about average rate of change before. That is just another way of saying slope. And so we know to find slope, you want to find your change in y over change in x, or change in something compared to change in something else. On this problem, they want us to find the change in area of a square. Okay, so instead of y on this problem, it's going to be change in area. That's what we're looking at first. With respect to the length of one of the sides x, as x changes from 4 to 5, or it looks like we got some other things too. So one thing we know is if we're looking at a square, like we got a picture over here, all the sides are going to be the same in a square. So we're looking at what happens as that side length changes. So our change in x, what happens to the change in the area? So how does the area change with respect to what the side length is? So we're going to find this just like we would slope then. We want to find what's the change in the area with respect to change of the side. So what we want to do is figure out, okay, if we have a rectangle, or not a rectangle, but a square, how do we find the area? Well, it would be like a rectangle. You want to take length times width. In this case, the length and width are identical. So we'd be multiplying x times x, or x squared. And so when we calculate out our areas, we'd want to be doing x squared. And when we do our side length, we're just doing whatever that x is. So let's do part A here. What is the average rate of change of area with respect to the side length? So what we want to do is find what is what is our area at 5 minus our area if the side length's 4 over 5 minus 4. Well, what would our area be if we plugged in 5 or had a side length 5? Well, our area would be 5 squared, or 25. If our area is 4, or our side length is 4, then our area is 4 squared, or 16. So now our equation over here would become, erase some of this, we got 25 minus 16 over 5 minus 4. And simplifying that out then, that would give us 9 over 1, or just 9. So the average rate of change is that our area is changing 9 units squared, whatever these units would be, because they're our top number's area over whatever that unit is. So it'd be changing at 9 units per unit squared per unit. All right, let's see what would it be if we went from 4 to 4.5 now. So now we want to find what's the area at 4.5 minus the area at 4 over our side length changing from 4.5 to 4. So similar on the bottom, if we subtract those, we get 0.5. On the top, we want to find those areas. We already know area at 4 is 16. What would our area be at 4.5? So what we'd want to do is figure out what is 4.5 squared to get that area. And that would be 20.25. So now if we subtract that and divide by 0.5, what do we get? And here we get minus 16 divided by 1/2, or 0.5. And the rate of change here now is 8.5 units squared per unit. Let's do one more. What is our rate of change from 4 to 4.1? So again, what's our area at 4.1? Minus what's our area at 4 over 4.1 minus 4. And we would get, if we square 4.1, we would get 16.81 minus, again, we know our area at 4 is 16, and if we subtract the bottom, we're going to get 0.1. Now, if we subtract that and divide, it turns out that it equals a rate of change of 8.1. Well, what we have here, it's similar to what we've looked at before when we started looking at some stuff with limits. All these numbers are the same. What's happening to our other length? It's getting closer and closer to also approaching 4, and then that would be what a derivative is. When your limit keeps going, that change just keeps going smaller and smaller, what do you get? Well, looking at our numbers here, it appears that these are probably getting closer to, looks like 8, right at a length of 4. So that would be our average rate of change. Let's just show that again. We haven't done one of these for a while, but let's look at what that instantaneous rate of change would be then. So then we would look at what is the limit as h approaches 0 of f, or in this case, let's use the variable we've been changing, area, as x plus a little bit minus the area at x all over h. Okay, so we want to figure out what are we going to get with this limit here. So our formula again is that area equals x squared. So if we continue this limit then, if we put x plus h in that, it'd be x plus h squared minus, our formula for area here is just x squared all over h. If we multiply that out, make sure I get my limit symbol in here. If we multiply this out and FOIL that out, it'd be x squared plus 2xh plus h squared minus the x squared we already have. Looks like these cancel. We can factor out an h out of what's left. And those h's are going to cancel on top and bottom. Now if we plug in 0 for h, our limit is 2x. And we know that what this found here was the derivative. This would be the derivative of the area with respect to the side length. So what we found here is what's the derivative of a of x would equal 2x. And that should be somewhat easy to find now that you guys do know derivatives. If we go back to our area formula over here, you're just using simple exponent rules. We know if we bring down the 2, the new power is 1, we get that same derivative of 2x. But what that tells us is the area with respect to the side length is changing at 2 times the side length. So if we wanted to find out what is the instantaneous rate of change when x equals 4, now we'd want to find what's the derivative at 4. And it would equal 8, meaning the area is changing at 8 times the side length as the side length grows. So rates of change tells you how fast something is changing with respect to something else. All right, our next problem. They say a pebble is dropped into a lake, creating a circular ripple that travels outward. So if you've ever been on like a lake or something and you drop a pebble in, you've seen these circles that keep rippling outward from where the object went into the water. And what they say about this is that ripple travels outward. Let A be the area of the outer circle. So that first circle that comes out, A is going to be the area of that circle. Find the instantaneous rate of change of the area with respect to the radius of the circle. So what we want to figure out is, okay, what's our equation on this one? What is the area of that outer circle going to be? Well, from geometry, you should know that area of a circle is pi r squared. So our function here, our area, is a function of the radius. okay, because that's the variable on the other side. So if we want to find the instantaneous rate of change, the change at a particular moment when the radius is something, we'd want to find derivative. We could go through and do a limit definition like we did on the last one, but now that you guys are familiar with derivative rules, let's stick with that. So derivative now, or instantaneous rate of change of the area with respect to the radius would be, using our power rule on the other side, bring down the 2. R is now going to have a new power here of 1, and we don't necessarily need to write that 1. So that would be the instantaneous rate of change formula for a circle. So now if we wanted to find out what that is at any time, we should be able to do that, and that's what our next question is asking. It says calculate dA dr when r equals 3 and explain its meaning. So this is saying what's the change in A with respect to the change in R. And so dA dr, that's just another way of writing the derivative of A with respect to R. These two mean the same. They're saying the same thing. Okay, so if we want to find what is dA dr when r equals 3, we can write it like that in that notation, or we could write it as derivative of A at 3, but ultimately we want to be plugging that in to our equation, and that the equation we had from the previous slide was that the derivative of the area was with respect to the radius, or this was equal to 2 pi r. So now if we want to find that at 3, we want to plug 3 in for the radius. And so the area is changing at a rate of 6 pi when the radius is 3. The area is changing at a rate of 6 times pi. We could estimate, so we kind of have a better idea of what that's saying. If we multiply 6 times pi, it's approximately 18.8, 8.5 here. So the area is expanding at 18.85 feet squared because it's an area. That's how fast it's expanding when the radius is 3. When the radius is 3 feet. So this would be how fast the area is growing when the radius is at a radius of 3 feet. That's what we're finding. That's what that means. Okay, next one says, show that the rate of change of the area of a circle with respect to its radius at any radius is equal to the circumference of a circle. So again, they're talking about area of a circle again. So it's the same equation we just had. Area equals pi r squared. And we know if we took the derivative like we did before, dA dr would be equal to 2 pi r. And so they want us to show that that is equal to the circumference of a circle. So we know area of a circle we just found was pi r squared, where this r is the radius. How do you find circumference again? Well, circumference is if you have the diameter, if you measure that same diameter around, there's 1, 2, 3 plus a little bit more diameters that go around a circle. So there's pi, that meaning pi diameters around a circle. So circumference is pi times diameter. Hopefully you kind of remember that from geometry. Well, also, what do we know diameter is the same as? Diameter is equal to 2 radiuses, so circumference is also pi times 2 radiuses, and that is the same equation that we have here. Circumference is 2 pi r, change in area with respect to the radius is also 2 pi r. And that's not a coincidence. There's a lot of stuff with circles like that, and that's where some of these equations come from, as we'll start seeing as we get farther into calculus here. All right, one final one. Show that the rate of change of the volume of a sphere is equal to its surface area. So if we have a sphere with a radius r, what is its volume going to be? So what I want you to do here, see if you can think of in your group, or if you can't think of it, look it up. What is volume of a sphere? So pause the video if you need a moment. All right, let's see what you came up with. Hopefully you remember this from geometry, otherwise you should have been able to look it up. Volume of a sphere ends up being 4/3 pi r cubed is how you find volume of a sphere. They want us to show that this is equal to its the rate of change is equal to its surface area. So what we want to find is what is dV dr? What's the rate of change of the volume with respect to the radius? So let's take the derivative of the other side. Bring down the 3, and the new power should be 2. If we multiply 4/3 times 3, that would tell us, looks like those 3's would actually cancel out there. So we get 4 pi r squared. How do you find surface area of a sphere, the outside area around that? Well, if you look it up, surface area of a sphere is 4 pi r squared. So that is also not a coincidence. Rates of change, as you'll see as we go throughout this class, you can come up with a lot of those formulas that you saw in geometry. There's relationships between volume and surface area of shapes like we got here. The rate of change of volume is equal to the surface area of a sphere. Okay, so what you're going to do is work on those motion problems that we looked at yesterday with problems 1 and 2 that we were already assigned. Also, I want you to try 11 through 16 here, looking at rates of change with geometry problems. All right, try them out.